Hi guys, it's Daniel here, and today we're going to do 2011 AMC12B number 24. This problem looks quite intimidating at first, but it actually isn't that hard. Let pz equal z to the power of 8 plus 4 root 3 plus 6 z to the power of 4 minus 4 root 3 plus 7. And then once you graph this on the complex plane, you want to find the minimum perimeter of the octagon, all the octagons that can be formed using these roots on the complex plane as vertices. So, of course, to solve this problem, you will need to find the roots of this polynomial. And thankfully, when we look at this, it turns out there's only a z to the power of 8 term, a z to the power of 4 term, and a z to the power of 0 term, which basically just means that this is a quadratic in z to the power of 4. So we could use the quadratic formula, but even better, since we can notice that 4 plus root 3 plus 4 root 3 plus 6 differs from 4 root 3 plus 7 by 1, that this actually factors. It's a little too skinny. So pz actually factors as z to the power of 4 minus 1 times z to the power of 4 plus 4 root 3 plus 7. So if you expand this, you'll find that the z to the power of 4 z to the power of 4 gives z to the power of 8. And then you have a minus z to the power of 4 plus 4 root 3 plus 7 z to the power of 4, which gives plus 4 root 3 plus 6. And then negative 1 times 4 root 3 plus 7 gives minus 4 root 3 plus 7, so it works out. So now this is a much easier form that we can deal with, because both z to the power of 4 minus 1 and z to the power of 4 plus 4 root 3 plus 7 are relatively easy to handle. First, we can look at z to the power of 4 minus 1. These are simply the fourth roots of unity, which means that the roots will be here, 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 and here. That is 1, I, negative 1, and negative I. And of course, these lengths are 1s. So now we know z to the power of 4 minus 1 where the roots are. Now we have to find z to the power of 4 plus 4 root 3 plus 7, which is slightly more difficult. For this, we can use a more general form. Where are the roots of z to the power of 4 plus a? So if we look at z to the power of 4 plus 1, it might give us some intuition. Well, if we want to find the roots of z to the power of 4 plus 1, we just write it as z to the power of 8 minus 1 over z to the power of 4 minus 1. And this is just the 8th roots of unity, not including the 4th roots of unity, which means that the roots here are right here, where this is 1, this is 1, and these are all 1. And in particular, if we have z to the power of 4 plus a to the power of 4, then solving this gives not a distance of 1, but a distance of a. So that means whatever the roots of these are, it has a distance a equals the fourth root, 4 root 3 plus 7. So now the question is, what is the value of the fourth root of 4 root 3 plus 7? So first, to find the fourth root, let's just take two square roots. So for the first square root, it's relatively easy to find the value. If we let a plus b root 3 be the root of 4 root 3 plus 7, then this squared is equal to 4 root 3 plus 7, like this, and you quickly find that a equals 2, b equals 1. So now we have to find the square root of 2 plus root 3. And this is where things get slightly more complicated, because if we try to use this method, it doesn't quite work out because a and b turn out to not be integers. However, let's try actually just doing this method once again and see what happens. So this thing squared is equal to 2 plus root 3, which means that if we square this, we get a squared plus 3b squared plus 2ab root 3, which is equal to 2 plus root 3. And so we know that a plus 3b squared is equal to 2, and 2ab is equal to 1. So this is equal to 2. Let's see. let's erase this. This is equal to 2, and this is also equal. So we can first cancel out this root 3, of course. So this is just 1. And now we have to solve AB equals 1/2 and a squared plus 3b squared equals 2. Now, you can solve this by just noticing that if we multiplied the right-hand side of each of these by 2, so if this was 4 and this was 1 instead, then a equals b equals 1 would work. So if we divide by 2 back, then this gives a equals b equals 1 over root 2. And this is in fact the solution of the system. But if you can't notice this, you can just use substitution and then solve the quadratic for a or for b, and you'll get the same thing. So the point is that this thing is just equal to the square root of 1/2 plus the square root of 3/2. So now we know the value of a, so let's draw everything on one diagram. So here is the roots of z to the power 4 plus 4 3 plus 7, where this distance is equal to square root of 1/2 plus square root of 3/2. And now we have to find this distance. What is this distance? To do this, we can use the Pythagorean theorem. So let's draw this thing and this height. So we want to find these two leg distances. Well, first of all, if this distance is square root of 1/2 plus square root of 3/2, that means since this is a 45, 9 degree triangle, that the distance of the length of this leg is equal to square root of 1/2 plus square root of 3/2 over square root of 2, which is just equal to 1/2 plus square root of 3 over 2. Meanwhile, we can see that this thing is also the same thing, this distance. So that means this distance is just equal to 1 minus 1/2 plus square root of 3 over 2, which is just equal to 1/2 minus square root of 3 over 2. Now we have the lengths of the two legs. We can use Pythagorean theorem to get that this distance is just equal to, well, if you square both of these and add them together, then the 2ab term of the a squared plus 2ab plus b squared part cancels out, and you're just left with 2 times this thing squared plus this thing squared. So that's just equal to 2 times 1/4 plus 3/4, which is equal to 2. And then remember, we have to take the square roots. So this length right here is just equal to the square root of 2. And by symmetry, the lengths of all the sides of the octagon are square root of 2. So that means the total perimeter is 8 square root of 2, which is right here. So that is our answer, and we are done.
Hey guys, I'm here back with another math video. Today we're going to be doing a relatively simple logarithm problem. This is from Mandelbrot